And the text, of course, understand the English, but that's a lot of numbers and stuff. You need to be study computer science on a university to understand this, or be a professional computer programmer or some kind of experts. Let's take some cola. It's Saturday evening, and every day I make a video about Ukraine, about this war in Ukraine. This day 108 today, so I have to make a video after this one. But I think I finish this, then I will do this Danish Ukraine video day 108. Then maybe I'll do one more later tonight, because there's many hundred PDF, and I just download more about France, Germany, Bulgaria, Spain and Switzerland. And I did download more computer, but I just stick to my list. Right now. So, but every time I add a little bit more to the list. But now I got started again with do all this X86. Then I just continue there. Do an inline pack micro personal computers. But of course I not understand anything of all this. I understand the language, of course. I understand the English. But that's too much information. And I have to go to the Wikipedia and look this. There's a lot of stuff. All this MMX and all these instructions. I don't like to scroll back right now. I can do it when I'm finished. But we still have this 15 pages. But there could be like maybe 7-8 pages references. So I don't think that's so much left.
Addresses and other selector details were dramatically reduced. In addition, an addressing mode was added to allow memory references relative to RIP, the instruction pointer, to ease the implementation of position-independent code, used in shared libraries in some operating systems. 128-bit. SIMD registers XMM0, XMM15. 256-bit. SIMD registers YMM0, YMM15. 512-bit. SIMD registers ZMM0, ZMM31. Miscellaneous / special purpose. X86 processors that have a protected mode, i.e. the 80286 and later processors, also have 3 descriptor registers, GDTR, LDTR, IDTR, and a task register, TR. 32-bit X86 processors, starting with the 80386, also include various special / miscellaneous registers such as control registers, CR0 through 4, CR8 for 64-bit only, debug registers, DR0 through 3, plus 6 and 7, test registers, TR3 through 7, 80486 only, and model-specific registers, MSRs, appearing with the Pentium O.AVX512 has 8 extra 64-bit mask registers for selecting elements in AZMM. Purpose. Although the main registers, with the exception of the instruction pointer, are general purpose in the 32-bit and 64-bit versions of the instruction set and can be used for anything, it was originally envisioned that they be used for the following purposes: L/R/AX/EAX/racks, accumulator. CL/CH/CX/ECX/RCX, counter, for use with loops and strings. DL/DH/DX/EDX/RDX. Extend the precision of the accumulator. For example, combine 32-bit EAs and DDX for 64-bit integer operations in 32-bit code. BL/BH/BX/EBX/RBX, base index, for use with arrays. SP/ESP/RSP, stack pointer for top address of the stack. BP/EBP/RBP, stack base pointer for holding the address of the current stack frame. Psi/ESI/RSI, source index for string operations. DI/EDI/RDI, destination index for string operations. IP/EIP/RIP, instruction pointer. Holds the program counter, the address of next instruction. Segment registers CS, code. DS, data. SS, stack. S, extra data. FS, extra data #2. GS, extra data #3. No particular purposes were envisioned for the other 8 registers available only in 64-bit mode. Some instructions compile and execute more efficiently when using these registers for their designed purpose. For example, using L as an accumulator and adding an immediate byte value to it produces the efficient add to L opcode of 04H, whilst using the BL register produces the generic and longer add to register opcode of 80C3H. Another example is double precision division and multiplication that works specifically with the AX and DX registers. Modern compilers benefited from the introduction of the SIB byte, scale index base byte, that allows registers to be treated uniformly, mini-computer-like. However, using the SIB byte universally is non-optimal, as it produces longer encodings than only using it selectively when necessary. The main benefit of SIB byte is the orthogonality and more powerful addressing modes it provides, which make it possible to save instructions and the use of registers for address calculations such as scaling an index. Some special instructions lost priority in the hardware design and became slower than equivalent small code sequences. A notable example is the LODS instruction. Structure. General purpose registers, A, B, C and D, 645648403224168R, XE, X, X, H, L. 64-bit mode only general purpose registers, R8, R9, R10, R11, R12, R13, R14, R15, 645648403224168. D, W, B. Segment registers, C, DS, E, F and G, 168, S. Pointer registers, S and B, 645648403224168R, P, 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 PL. Note, the PL registers are only available in 64-bit mode. Index registers, S and D, 645648403224168R, IE, IL. Note, the IL registers are only available in 64-bit mode. Instruction pointer register, I, 645648403224168 RIP IPIP. Operating modes. Real mode. Real address mode, 32, commonly called real mode, is an operating mode of 8086 and later X86 compatible CPUs. Real mode is characterized by a 20-bit segmented memory address space, meaning that only slightly more than 1 MB of memory can be addressed. p. Direct software access to peripheral hardware, and no concept of memory protection or multitasking at the hardware level. All X86 CPUs in the 80286 series and later start up in real mode at power on. 80,186 CPUs and earlier had only one operational mode, which is equivalent to real mode in later chips. On the IBM PC platform, direct software access to IBM BIOS routines is available only in real mode, since BIOS is written for real mode. However, this is not a property of the X86 CPU but of the IBM BIOS design. In order to use more than 64 kilobytes of memory, the segment registers must be used. This created great complications for compiler implementers who introduced odd pointer modes such as near, far and huge to leverage the implicit nature of segmented architecture to different degrees, with some pointers containing 16-bit offsets within implied segments and other pointers containing segment addresses and offsets within segments. It is technically possible to use up to 256 kilobytes of memory for code and data, with up to 64 kilobytes for code, by setting all 4 segment registers once and then only using 16-bit offsets, optionally with default segment override prefixes, to address memory. But this puts substantial restrictions on the way data can be addressed and memory operands can be combined, and it violates the architectural intent of the Intel designers, which is for separate data items, for example arrays, structures, code units, to be contained in separate segments and addressed by their own segment addresses, in new programs that are ported from earlier 8-bit processors with 16-bit address spaces. Unreal mode. Unreal mode is used by some 16-bit operating systems and some 32-bit bootloaders. System management mode. The system management mode, SMM, is only used by the system firmware, BIOS/UEFI, not by operating systems and applications software. The SMM code is running in SRAM. Protected mode. In addition to real mode, the Intel 80286 supports protected mode, expanding addressable physical memory to 16 MB and addressable virtual memory to 1 GB, and providing protected memory, which prevents programs from corrupting one another. This is done by using the segment registers only for storing an index into a descriptor table that is stored in memory. There are 2 such tables: the global descriptor table, GDT, and the local descriptor table, LDT, each holding up to 8,192 segment descriptors, each segment giving access to 64 kilobytes of memory. In the 80,286, a segment descriptor provides a 24-bit base address, and this base address is added to a 16-bit offset to create an absolute address. The base address from the table fulfills the same role that the literal value of the segment register fulfills in real mode, the segment register shave being converted from direct registers to indirect registers. Each segment can be assigned one of 4 levels used for hardware-based computer security. Each segment descriptor also contains a segment limit field which specifies the maximum offset that may be used with the segment. Because offsets are 16 bits, segments are still limited to 64 kilobytes each in 80,286 protected mode. 33. Each time a segment register is loaded in protected mode, the 80,286 must read a 6-byte segment descriptor from memory into a set of hidden internal registers. Thus, loading segment registers is much slower in protected mode than in real mode, and changing segments very frequently is to be avoided. Actual memory operations using protected mode segments are not slowed much because the 80,286 and later have hardware auto-check the offset against the segment limit in parallel with instruction execution. The Intel 80,386 extended offsets and also the segment limit field in each segment descriptor to 32 bits, enabling a segment to span the entire memory space. It also introduced support in protected mode for paging, a mechanism making it possible to use paged virtual memory, with 4 KB page size. Paging allows CPU to map any page of the virtual memory space to any page of the physical memory space. To do this, it uses additional mapping tables in memory called page tables. Protected mode on the 80,386 can operate with paging either enabled or disabled. The segmentation mechanism is always active and generates virtual addresses that are then mapped by the paging mechanism if it is enabled. The segmentation mechanism can also be effectively disabled by setting all segments to have a base address of 0 and size limit equal to the whole address space. This also requires a minimally sized segment descriptor table of only 4 descriptors, since the FS and GS segments need not be used. Q. Paging is used extensively by modern multitasking operating systems. Linux, 386 BSD and Windows NT were developed for the 386 because it was the first Intel architecture CPU to support paging and 32-bit segment offsets. The 386 architecture became the basis of all further development in the X86 series. X86 processors that support protected mode boot into real mode for backward compatibility with the older 8086 class of processors. Upon power on, aka booting, the processor initializes in real mode, and then begins executing instructions. Operating system boot code, which might be stored in read-only memory, may place the processor into the protected mode to enable paging and other features. The instruction set in protected mode is similar to that used in real mode. However, certain constraints that apply to real mode, such as not being able to use XCXDX in addressing, do not apply in protected mode. Conversely, segment arithmetic, a common practice in real mode code, is not allowed in protected mode. Virtual 8086 mode. There is also a submode of operation in 32-bit protected mode, aka 80,386 protected mode, called Virtual 8086 mode, also known as V86 mode. This is basically a special hybrid operating mode that allows real mode programs and operating systems to run while under the control of a protected mode supervisor operating system. This allows for a great deal of flexibility in running both protected mode programs and real mode programs simultaneously. This mode is exclusively available for the 32-bit version of protected mode. It does not exist in the 16-bit version of protected mode, or in long mode. Long mode. In the mid-1990s, it was obvious that the 32-bit address space of the X86 architecture was limiting its performance in applications requiring large data sets. A 32-bit address space would allow the processor to directly address only 4 GB of data, a size surpassed by applications such as video processing and database engines. Using 64-bit addresses, it is possible to directly address 16 EIB of data, although most 64-bit architectures do not support access to the full 64-bit address space. For example, AMD 64 supports only 48 bits from a 64-bit address, split into 4 paging levels. In 1999, AMD published a nearly complete specification for a 64-bit extension of the X86 architecture UHIC they called X86-64 with claimed intentions to produce. That design is currently used in almost all X86 processors, with some exceptions intended for embedded systems. Mass-produced X86-64 chips for the general market were available 4 years later, in 2003, after the time was spent for working prototypes to be tested and refined. About the same time, the initial name X86